Hello everyone, this is our beta paddleboard gyro-stabilizer presentation. I'm John Barnes, along with my groupmates James Delamano, Thomas Jacoby, Carson Plez, and Andrew Moeller. A quick objective recap is that we want our device to act like training wheels would on a child's bike, but for a paddleboard, so that kids with this new thing can learn while not being discouraged from the sport altogether. The device will provide a restorative moment under the conditions where it's rolling side to side. We have requirements where the box must be waterproofed so that nothing gets to the device to ensure safety of the children using this. It also must be user-friendly and easy to put onto and remove from the paddleboard.
Regarding the schedule for our project, everything was finished on time. Aside from one task, we didn't get a chance to put the ballistic protection in our design due to the recent COVID-19 outbreak. But other than that, all of the different assembly and purchasing materials was all completed right on task.
Here's a blueprint design of the final assembly. We have the battery, controller, and potentiometer within the brackets that make the frame. There is now an open U-bracket containing the bigger steel flywheel compared to the original closed design to hold the smaller aluminum flywheel in the Alpha prototype. This is a design progression between the old semester 1 design on the left and the Alpha design on the right. There are different straps now on the beta, and the sizes are exact in both models. This is another comparison between the semester 1 design and the Alpha design. The arbor adapting bracket is still on the gyroscope in the beta, which is a major change from the semester 1 design to the Alpha prototype. This connects the motor to the flywheel in a more reliable and structurally sound way. Here's a final rendering of what it looks like on the paddleboard. Overall, the focus on the beta phase was on refinement and improvement of our product. We took the feedback and lessons learned from past development and now have a very good final prototype. This is how the device realistically looks like within the box on the wood frame we had to build for it. The biggest improvements were the steel flywheel for more weight, remote start and stop, wire management, and waterproofing. Additional improvements that were still very important were rubber bands and tabs that were built in to prevent gimbal lock, as you can see on the top, and dampening pads were put on the bottom of the frame to minimize noise. Here's another picture of how it looks like in the box. Here, high-strength suction cups are attached to the box to provide a non-invasive solution to mounting. And here's a real-life picture of a person on a child's paddleboard with a stabilizer.
One of the first analyses that we did in the first semester was a buoyancy force analysis to calculate the restorative moment that you get from a paddleboard alone. The picture on the left is a volumetric calculation to show the entire volume of the paddleboard to be used in later calculation. We then fully submerged it to ensure that our volume calculation was accurate, and we got back a buoyancy force that was comparable to their recommended weight. We then tilted the paddleboard, as it can be seen in the lower middle picture, to a critical angle of roughly 8 degrees, which was determined and agreed upon that this would be a crucial point where the paddleboard then would most likely have the person fall off of it. With this, we had a max stabilization of roughly 5 foot-pounds, and this led us to a gyroscopic required stabilization of roughly 10, which would be a 200% increase over a standard board alone.
So the main purpose of the gyroscopic force analysis, which was our second analysis, by the way, was to find the mass moment of inertia and revolutions per minute of the flywheel required to generate the desired torque, that 10 foot-pound torque that John talked about previously. The biggest assumption that we made was the precession rate of the gyroscope itself was 90 degrees per second, and this is critical when talking about the torque provided, because the governing equation stipulates that the torque is equal to the mass moment of inertia times the angular precession rate times the angular rate of the flywheel spinning. And so with those governing equations, we went ahead and did a parametric analysis And the parametric analysis allowed us to plot for different torques the optimization lines that represent each torque along every curve here. So for example, this point here represents an RPM of 6,000 and a mass moment of inertia of looks like right under 0.02 kilograms per meter squared. And what that means is that it requires 6,000 RPMs and right under 0.02 kilograms per meter squared in order to generate that 10 foot-pounds of resistive torque. And so with our actual beta prototype, we found that the point of interest wasn't too far off from our originally projected point here. It's actually at 5,500 RPMs, and the mass moment of inertia is right at 0.0134 kilograms per meter squared. And from here, you can look and see the projected final specs on the side, and the ultimate torque generated was around 9.93 foot-pounds.
The third important analysis that we conducted was a finite element analysis of the structure here. You can see from this diagram that most of the stress is concentrated around the shaft of the motor. In the alpha and the beta prototype designs, we have mitigated this by including an arbor shaft to connect the flywheel to the motor, so that kind of bolsters up the shaft size there. And the minimum factor of safety for this device is about 1.43, which is deemed allowable. Another analysis that we conducted was a failure modes and effects analysis. We're not showing it on a slide here, but just to know that we conducted it, we found out some of the major things that could go wrong with our apparatus, and we found ways to mitigate that.
This is our testing apparatus with the alpha on it. We like these videos because it clearly shows the precession rate of the gyroscope on the right-hand side while it is on. So there is a 5-pound hanging mass for this test, and as it can be seen with the gyroscope off, on the left-hand side, it falls straight down, whereas on the right-hand side, the gyroscope is on and it falls more slowly. We understand that the quality of these videos may be a little choppy, but it is still clear that this slows down the rotation of the paddleboard simulated testing apparatus.
And here's some videos of the beta prototype undergoing testing. As you can see on the left here, it's with the gyroscope off, and on the right, it's with the gyroscope on. You can tell, as in the previous slide, that the tests with the gyroscope on, the apparatus turns much more slowly. It is important to note in these tests that for the beta prototype, we used a 15-pound hanging mass, whereas in the alpha prototype, we used a 5-pound hanging mass. So that's why it might appear to move more quickly, but it's just due to the difference in weight. And here is a testing explanation. So we have several governing equations. The torque is equal to the moment of inertia times the angular acceleration. The applied torque, we can calculate that very easily. We know the radius of the spool of our apparatus, and we know the weight of the test weight, so we can figure out how much torque we apply to the system. And the angular acceleration is something that we measure from the linear acceleration determined by the photo gates divided by the radius of the spool. Using these values, we can figure out how much restorative moment that the testing apparatus, that the gyroscope provides.
So from those tests, we found that for the steel flywheel, the maximum torque that it could generate was around 10.4 foot-pounds, and that was for a 20-pound hanging mass. As you can see, we varied the hanging mass from 5 pounds all the way to 20, and the corresponding values associated with that are plotted here on this chart. In addition, we also have the 3.8 foot-pound result from the aluminum flywheel, and that was also at a hanging mass of 5 pounds. So you can see that there was a definite increase from the aluminum flywheel to the steel flywheel, and that's why we made that choice, was because we knew that the steel flywheel would ultimately generate a larger resistive torque. And if you look at the picture on the right here, it just shows the original alpha and then the beta with all the different components added. And next. So what? So the test result is actually 100%, it's actually greater than 100% of what our target specification was. So our goal was 10 foot-pounds, and we actually, from our tests, we can now deduce that the gyroscope apparatus does generate at least 10 foot-pounds, and it could generate more if the input torque is actually increased. So with that, another thing that we wanted to reiterate was that the beta steel disc actually did increase the stabilization torque, and that was talked about previously. And then one final thing, the parametric analysis that we did the first semester, from that analysis, which assumed a precession rate of 90 degrees per second or pi/2, the projected torque was around 8.93 foot-pounds. And if we increase that precession rate assumption to around 100 degrees, the results are almost spot on with what the test results concluded. So in other words, it verifies the validity of our calculations, the test does at least, and we were right. So it's really nice to see those results.
We revisited the cost analysis this second semester to do some slight changes in how much it was going to cost overall to produce this product and how much we had to spend on it. So for the total manufacturing costs, we came up with a total cost per unit of approximately $270, with the overhead being about $70. That leaves us to have an asking price for anywhere from $300 to $350. If we were to sell this product for $350, we could generate about 25% profit, which is a pretty standard business model. So here's a more in-depth cost analysis for manufacturing. It's split into the mechanical, electrical, structural, and miscellaneous parts. And as you can see, we've got the quantity, the unit prices, all the machining, assembly, and labor. And that gave us a total cost per unit of approximately $270. So a good assumption that we made was we took all the assembly, machining, and labor costs and we multiplied them by 2 just to be safe. And that's what gave us our overhead of about $70. And like I said, the total cost per unit came out to about $270. So our actual budget for this project, we estimated that it was going to cost about $450 to produce our product. And you can see there it's split up into mechanical, structural, and miscellaneous parts. And our actual cost overall was about $425. So it was under budget, which is good. This does not include the purchase of a paddleboard for testing purposes.
So for the target specifications, we wanted to provide a little bit of a status update on our beta. And as you can see, there's a lot going on here because this incorporates the semester 1 value from our analysis, the alpha, and the beta. So we're just going to focus on the beta as of now. The beta, the weight of the board stayed the same from the very beginning. The weight of the battery in the control system is around 4 pounds for the smaller battery and 8 pounds for the larger battery. The weight of the gyroscope apparatus for the beta is actually 10 pounds. And the weight of all of it put together is around 26 to 30 pounds. And that, relative to our original value, is actually under our intended value, so it's really good. And next, the stabilization without the gyroscope is 5 pounds. That was from the buoyancy force analysis. The max gyro stabilization torque that we tested or found was 10.4 foot-pounds, and that was also within our intended value range. The surface area of the gyroscope apparatus on the paddleboard is around 2 square feet, and that's also within our original intended range. The full the adjustability increments range from 1,000 to 6,000 RPMs, which is slightly under what we originally intended, but that was just based on the limitations from the motor. And it does have full range adjustability with that potentiometer knob that Carson talked about. The max weight and balance longitudinally and laterally, those are very dependent on the positioning of the apparatus on the paddleboard. So it's relatively, I guess, insignificant, as to say. It just depends on where you place it and how you place it on the board. The time to remove or attach was timed at 4 minutes and 30 seconds, which is under our original value of 5 minutes. The ease of adjustment, we actually came to the conclusion that that's a 9 out of 10, and the reason for that being that it's remote start and stop, and the potentiometer allows for full range of adjustability. So with those two things, we thought it was pretty good on those standards. And the overall cost of the team was around $725, but that includes the paddleboard, as Bryce talked about earlier with the cost or budget. So realistically, without the paddleboard and COVID-19 stepping in the way, we would have had a cost around $425 because we would have just rented a paddleboard from SIUe or some other place without having to buy one straight out. And then the safety container tensile strength, that was left to be determined because we didn't actually get the ballistic nylon protection. Bryce mentioned that earlier in the second slide, I believe. And
so for our semester 2 device, our beta prototype here, we do have a successful device. It does provide a maximum resistive torque of about 10 foot-pounds under the rolling motion of a paddleboard. It has a 2-hour battery life. It's fully rechargeable. If we chose to implement the larger battery, that would give us about 3 hours of battery life, but I think the smaller one is just fine. 2 hours is plenty. It also has our remote control start and stop, which allows for ease of use for the paddleboard riders, especially when they are on the paddleboard. And it is attachable and detachable within 5 minutes, which is another one of our target goals.
Further developments in design were thought of, however, was not necessarily realistic due to the pandemic. For example, we could use a control moment gyroscope similar to the picture on the right to provide levels of assistance for the rider to let the rider learn more smoothly. Ballistic protection again was in the works, however, could not have been done due to the recent events. We could also drill precise holes in the flywheel to maximize the mass moment of inertia compared to weight. And the balancing of the flywheel is always something that could be done better, but that's simply up to what kind of equipment we had accessible. And we look forward to answering your questions or go more in depth in the Zoom meeting, and we thank you for your attention.